Hello everyone, we are solving question number 51 of GATE 2022 Chemical Engineering paper, and this question is related to the subject of fluid mechanics. The question states, two reservoirs located at the same altitude are connected by a straight horizontal pipe of length 120 meter and inner diameter 0.5 meter as shown in the figure. A pump transfers the liquid of density 800 kg per meter cube at a flow rate of 1 meter cube per second from reservoir 1 to reservoir 2. The liquid levels in reservoir 1 and reservoir 2 are 2 meter and 10 meter respectively. Assume that the reservoir's cross-section areas are large enough to neglect the liquid velocity at the top of the reservoir. All the minor losses can be ignored. The acceleration due to gravity is 9.8 meter per second square. If the friction factor for the pipe is 0.01, the required power of the pump rounded off to one decimal place is dash. So in this question, we have been given two reservoirs and we have been asked to find how much power will be required by this pump to deliver the fluid from reservoir 1 to reservoir 2, considering all the minor losses as negligible. Then all the other parameters we have been given, that friction factor is also 0.01, and ultimately we have to find the power required by the pump. So over here we have been given the length of the pipe is 120 meter. That is, length is equal to 120 meter. The inner diameter of the pipe is 0.5 meter. Let's call it as D as 0.5 meter. The density of the fluid rho is 800 kg per meter cube. The flow rate in volumetric flow rate is 1 meter cube per second. Then we have been given the respective heights 2 meter and 10 meter. That is, h1 is equal to 2 meter, h2 is equal to 10 meter. Let's just call it, this is reservoir 1, this is reservoir 2. Then gravitational acceleration due to gravity is 9.8 meter per second square, and the friction factor F is 0.01. So we can write the Bernoulli's equation across this point 1 and 2, which will give us this equation. P2 minus P1 upon rho, where P2 is the pressure for this reservoir 2 at the discharge of the pump, and P1 is the pressure at the suction of the pump. That is P2 minus P1 plus G Z2 minus Z1 plus half V2 square minus V1 square plus friction losses plus the work done required by the pump. This will be equal to 0. Now over here, the inner diameter of the pipe remains constant, that is 0.5 meter. That is, the velocity at both this point 1 and 2 will be same. That is, we can neglect this term. Also, the P2 and P1 both are open to atmosphere. So we can also neglect this P2, and so they will be same, and we can cancel this first term also, that is P2 minus P1 will be 0. So now we are left with these three terms, and we have to find the power. For that we require the work done. So first let us calculate this friction loss. That is, this friction loss we can write it as 4FL V square upon 2D, where F is the friction factor, L is the length of the pipe, V is the average velocity, and D is the diameter of the pipe. Now over here we don't have this average velocity, so that we can calculate it as velocity as volumetric flow rate upon area, that is Q dot upon A. So we can write this as 1 meter cube per second upon the cross section area of the pipe will be pi by 4D square. Diameter is 0.5 square. So this will come around 5.09 meter per second. So this is the average velocity And based on that, we can calculate the friction loss. That is HF will be 4FLV square upon 2D. The value of F we have been given as 0.01. Length of the pipe is 120 meter. Velocity we have calculated it as 5.09 upon 2 times diameter. Diameter of the pipe is 0.5 meter. So again we can solve this, and the friction loss we will be getting it as 124.359. You can check the units and it will be meter square per second square. Now we can replace this HF in the earlier Bernoulli's equation. So we have G into Z2 minus Z1, that is basically 10 minus 2, that will be 8 meter plus HF plus W. So HF we have calculated it as 124.35 plus work done is equal to 0. That implies the work done will be minus of 124.359 plus 8 into 9.81. So that you can write 8 into 9.81, and ultimately it will come around 202.7. The unit will be same as the HF, that is meter square per second square. Now in the question we have been asked to find the required power of the pump. So power we can write it as mass flow rate into the work done. So it will be mass flow rate, we can simply multiply this volumetric flow rate by density, that is rho into Q dot plus W. So density we have been given it as 800 kg per meter cube, and the volumetric flow rate is 1 meter cube per second, and then the work we found out is 202.7. So this will come around 207 watt. No, this will be 162207 watt. And the final answer we can write it as 162.207 kilowatt. So yes, the final answer is 162.2 kilowatt.